Hello everyone. In the previous class, we have discussed about response spectrum method, which is a dynamic analysis method for estimating design seismic load on a given building. We have also seen how do we distribute the design seismic load vertically and in plane among various lateral load resisting elements. Today, we will illustrate the same using an example problem. We will use the same example problem which we have utilized for understanding equivalent static method. So, in this example problem, we have a 3-story hospital building to be constructed on a hard soil site in New Delhi. The building comprises of reinforced concrete, a special moment resisting frame in orthogonal directions, that is in both the directions. The plan and elevation details are shown over here, which means we have a 3-story building with a story height of 3.5 meter each. The way width is 4 meter in this direction and 5 meter in the other direction. The slabs are 125 millimeter thick and are monolithically cast with beams. The beams are 250 mm by 350 mm. The columns have cross section of 250 mm by 400 mm as shown over here. We have two types of masonry infill walls. The external infill walls have thickness of 250 mm and the internal infill walls have thickness of 150 millimeter. The floor live load is estimated to be 3.5 kilonewton per meter square, and we are assuming that there is no parapet wall on the roof, and using response spectrum method we need to determine the design lateral force on the highlighted internal frame of the building on this very frame, and we need to distribute it along the building height. We have also assumed the grade of concrete to be M25 and grade of reinforcing steel as Fe415. The unit weight of reinforced concrete and masonry infill are taken as 25 kilonewton per meter cube and 20 kilonewton per meter cube respectively. So, now let us get into the solution. For solving, we will first calculate the seismic weight of various floors, thereby to obtain the seismic mass at different floor levels, so that we can set our eigen problem. In the case of equivalent static method, we just needed the total seismic weight of the frame, but in case of response spectrum method, we need to find out the seismic mass at different floor levels and then set the matrices for mass and similarly set the stiffness matrix as well, so that we get our characteristic equation or the eigen problem. Then we shall be able to solve it for natural period and modes of oscillations. So, let us calculate the seismic weight at first and second floor levels first of all. So, in this case the self weight of slab is equal to 0.125 into 8 into 5 into 25. Here the slab is 125 millimeter thick. The dimensions in plan are 8 meter by 5 meter considering the tributary area. I hope by now you are familiar with why we are considering 8 into 5. We have discussed it in the example problem on equivalent static method as well. The unit weight of reinforced concrete is taken as 25 kilonewton per meter cube. Thereby, the self weight of slab comes to be 125 kilonewton. The self weight of beams is then calculated, where the cross section is 250 mm by 350 mm and the total length of beams is 2 into 4 for the frame, and for the tributary area you have the beams also coming into the picture. So, you have a total of 6 beams with 2.5 meter length. So, it is 3 into 5, and then 25 is the unit weight of reinforced concrete, giving us the self weight of beam to be 50.31 kilonewton. I understand that you must have gone through this example problem on equivalent static method by now, so that you can be very sure these calculations remain intact The cell weight of columns is also calculated as 26.25 kilonewton. If you have any problem understanding, you can go back to that problem as well based on equivalent static method and look into further description. Then the cell weight of infill wall is also calculated as 311.5 kilonewton. Now, the total dead load at the first floor level or the second floor level is calculated as the sum of all these, which comes to be 513.06 kilonewton. The live load at the first and second floor level is calculated as 3.5 kilonewton per meter square is the load intensity. The plan dimension for the trivet area of the frame which is under consideration is 8 into 5 square meter, and then you have 0.50 which represents that if your live load intensity is more than 3 kilonewton per meter square, how much contribution live load gives to the seismic load calculation? 50%. So that is why it is 0.5. So it gives us 70 kilonewton of live load at first floor level as well as on the second floor level. So taking the sum of dead load and live load, we get the seismic weight at the first and second floor level to be 583.06 kilonewton. If we divide this very value by g or the acceleration due to gravity, we shall be able to get the seismic mass at first floor level or the second floor level, which is found to be 59,435 kilograms. Now, once we know the seismic mass at first floor level as well as the second floor level, we shall also be able to find out the seismic mass at the roof level. How do you get that? Similar to the previous case, we have gone through the self weight and then dead load, live load and then the seismic weight. So the self weight of slabs and beams remain the same, while the self weight of columns and infill walls are actually reduced to half, because now the tributary area coming from column and walls is actually only on the lower side, only on the below the roof level. There is nothing above the roof level. So the self weight of columns and infill walls are reduced to half. Now the total dead load at the roof level is then calculated as sum of all these four values shown over here. This is obtained as 344 kilonewton. At the roof level, live load can be ignored based on the clause 7.3.2 of IS 1893 part 1 2016. Then the seismic weight at the roof level is now obtained as 344 kilonewton. If we divide it by G, we get the seismic mass at the roof level as 35,085.6 kilograms. So the total seismic mass of the frame you can calculate. However, this does not have much meaning as of now. So once we have the seismic mass at different floor levels known to us, we can set the matrix for mass. But before we get into the setting up of eigenvalue problem, let us also find out the different values of these factors. The seismic zone factor is equal to 0.24 because our site is located at New Delhi, which is in seismic zone 4. The importance factor is 1.5 given that it is a hospital building which needs to be operational in the aftermath of an earthquake as well. The elastic force reaction factor or the force reaction factor, sometimes also called as response reaction factor, shall have a value of 5 because the building comprises of reinforced concrete SMRF system. Now the references related to different tables of IS 1893 part 1 2016 are listed over here. Now we set up the mass matrix. How do we set up the mass matrix? We already know the value of M1, M2 and M3. We have calculated it. We just substituted in this way mass matrix. From where do you get this mass matrix? From the dynamics of multi-degree of freedom system. For that, you can look into the lectures 2.2 and 2.5. Okay. Now, how do you calculate the elastic stiffness matrix for the building frame? Now, here we have two things about the infill wall. The mass of the infill wall will always be considered in any kind of analysis. That is how we have obtained this mass matrix. As you remember, we have also calculated the dead load or the cell weight of the masonry infill wall. But when it comes to setting up of a stiffness matrix, then it is our choice whether we will ignore the effect of masonry infill or we will consider it. In this class, we will look into both the approaches. So, the first approach, which is ignoring effect of masonry infill, we are already looking into that. So, here the masonry infill wall does not contribute to the stiffness of the building. So, what is the elastic stiffness of a column? It is equal to 12 EI by h cube, where h is the height, I is the second moment of area, and E is the modulus of elasticity. So, that we calculated it over here, and then we found out that the elastic stiffness of each story shall be 3 times of this. Why 3 times of this? Because in the frame which we are considering currently, at any given story we have 3 columns. So, for one column, if the stiffness is 9330 kilonewton per meter, then we will multiply that with 3 to find the elastic stiffness of that story. Now, if we know the elastic stiffness of every story, then we can substitute the values as K1, K2 and K3 to obtain the stiffness matrix, okay, for the building frame. So, this we have obtained. Now, we can set up the eigenvalue problem, from where we get the characteristic equation, which is K minus omega square m. The discriminant will be equal to 0. If we solve the characteristic equation, we will get the natural frequencies of the system. What shall be the natural frequency? These are the cyclic natural frequencies omega 1, omega 2 and omega 3. The values are obtained over here. I am not going into detail of this, how do we do that, but I hope since you would have gone through a course on mathematics particularly related to eigen problem, then you must have understood how do we solve a characteristic equation of this type. Okay, once we have the value of omega 1, omega 2 and omega 3 known to us, we will calculate the natural periods corresponding to them, which are T1, T2 and T3. How do we calculate this? T equals 2 pi by omega, as simple as that. After finding out the natural period, for each natural period we shall find out the mode shape. Let us say for corresponding to T1 equals 0.576, the first mode shape is obtained, it is shown over here. Similarly, second mode shape and third mode shape. Now, at this point I would like to mention that how do you define that which is the T1 and which is T2. So, the fundamental mode is represented by the lowest cyclic natural frequency and the highest value of natural period. So, the highest natural period will be your T1 and the lowest natural period will be much further away. Now, we have been able to obtain the different mode shapes corresponding to different natural period. I suggest you look into a book on mathematics which gives you the solution of an eigen problem if you encounter any problem understanding this. Now, once we have the eigenvalue problem solved with us, that is, we know that what is the eigenvalue, that is the value of omega square, or instead we have taken it to the natural period, and then you have the modes of oscillation known to you, which are your eigenvectors. We shall also calculate the other two dynamic properties of the building, which are modal participation factor and modal mass. The expressions for modal participation factor and modal mass are given in the code IS 1893 part 1 2016 at relevant clauses. As you can see, these three modes, we have calculated the modal participation factor for all these three modes. For first mode, we have got the modal participation factor of 1.243, then for P2 and P3 as well. One thing what is very clear is that the magnitude of P1, P2, P3 goes on reducing, which means that the first mode is the mode which contributes majorly to the total oscillation of the building, and as we move to the higher modes, the effect becomes lower and lower, it gets diminished, and finally it becomes not so important for us. What is this negative sign indicating? The negative sign indicates that this mode will lead to oscillation in the opposite direction. Okay. Now let us look into modal mass. The expression is given over here, which is also available in IS 1893 part 1 2016, and from there we can calculate what is the percentage of mass of the building which is participating in any given mode. So, using the expression we have calculated M1 to be 92.5% of the total mass of the building. So, in the first mode 92.5% of mass participates. In the second mode M2 is equal to 10505.85 kg, which is roughly 6.82% of M1 plus M2 plus M3, which means that mode 1 and mode 2 combined is able to consider more than 99% of modal mass participation. The third mode has participation of only 0.67% of the mass. Now, since modal mass of the first mode itself exceeds 90% of the total seismic mass, in this case it is 92.5%, right. So, we can restrict our analysis only up to the first mode for designing lateral load calculation. However, in this problem we have considered all the three modes for the sake of understanding. So, after finding out these dynamic properties of building frame, we have gone to calculate the design lateral force at various floors in various modes. The expression is given over here. We have looked into this expression in the last class as well. So, what do we do? For mode 1, the natural period was 0.576 second. The soil was hard soil site. Based on that, we have found out the value of SA by G. SA by G came to be 1.736. This is based on this very plot, or there are expressions also available in IS 1893 2016. Then based on this SA by G, we shall be able to calculate the value of AH1, which is Z by 2 times of SA by G divided by R upon I. After substituting all these values, we get the value of AH1, which is further used to find out the design lateral force at ith floor in kth mode. Now, the value of modal participation factor for this mode is 1.243. Now, we have calculated this design lateral force at floor I in mode K, which means that it is for different floors in first mode. I am not going to explaining these calculations. I hope you are familiar with this from the last lecture as well. If you have any problem, please pause the video and confirm before you proceed. Then we have also done the similar stuff for mode 2 and mode 3. We have been able to find out the design lateral force at various floors in mode 1, mode 2 and mode 3 respectively. Once we have the design forces at various floors in various modes known to us, we can find out the story shear forces in various modes, right? Because if we start adding floor forces from top, then as we move down, we are able to find out the story shear forces in various stories. So, we do it for all the three modes, modes 1, 2 and 3, and these are shown over here. And then we combine all the modes through SRSS combination. Remember that the combination is applied on a story shear force and not on design lateral force or the floor force. So, the story shear forces in various modes are now combined as shown over here using SRSS combination to obtain these results. From these results, if we take the difference between story shears of consecutive story, we can find out what is the design lateral force at a floor between those two stories. I hope this is clear, because we have done the other way around in the example illustrating equivalent static method, where we were having the information about the design lateral force and then we had done the addition to obtain the story shear. From story shear we can again go back to the design lateral force. So, now we have done this, and this is for all the modes combined. So, based on this we can plot a schematic diagram as shown over here for design sizing force on various floors. As you can see, the maximum value is 37.52 kilonewton on the second floor. If we take the sum cumulatively, then we shall get the design story shear. For the top story, it should be 28.74 kilonewton. For the second story, it should be 28.74 plus 37.52, which gives us 66.26 kilonewton. And finally, the bottom story will attract a design story shear to be given by 66.26 plus 22.26, which gives us 88.52 kilonewton. Now, this is the process what we adopted while we ignored the effect of masonry infill. We will repeat the same process while considering the effect of masonry infill. Now, when we consider the masonry infill effect, our stiffness of the building frame will change, while the mass matrix remains the same, because mass matrix always considers presence of infill walls, but the effect of masonry infill is now being considered in the stiffness matrix as well. So, here the elastic stiffness of each column is found out in a very similar manner, and then the elastic stiffness of each masonry infill is also found out using the expression mentioned over here. And if you recall from lecture 2.5, we have a great description of how to find out the elastic stiffness of masonry infill. So, that is how we have been able to find that. We will not be discussing it into further depth as of now in this class, but you can always pause this video lecture to look into specific details related to this calculation. The calculation is self-explanatory. Now, the elastic stiffness of each story, how we will calculate that? So, for the given frame at any given story, you have 3 columns and 2 infill walls. Now, we have the knowledge of the values of elastic stiffness for columns as well as those masonry infills. So, based on that, we will sum it up 3 times of the elastic stiffness of each column plus 2 times of elastic stiffness of each wall to find out the elastic stiffness of each story. Now, once it is known to us, that is K1, K2 and K3 are equal to this value, we shall substitute that in this matrix form to find out the stiffness matrix. Now, we have the mass matrix and the stiffness matrix ready with us. What we can do? We can set the eigenproblem, solve the characteristic equation to find out the cyclic natural frequency and natural periods. Now, at this point, I would like to say that there is not much change in the natural period due to consideration or non-consideration of effect of masonry wall. So, again, after solving the characteristic equation, we are able to obtain natural period and various mode shapes, that is the modes of oscillations, which are shown over here. Again, I would like to reiterate at this point, which you might have the understanding from any course on structural dynamics, that the first mode will have one zero crossing which will be available at the base of the structure. The second mode shape will be having two zero crossing, so one at the base and the second somewhere between the first and second floor. How do you know that? Because there will be a change in sign of these very values in that case, in the event of zero crossing. Similarly, for third mode you have 3 such zero crossings. Now, once we have this information about dynamic properties, let us also calculate the other two dynamic properties, which are modal participation factor and modal mass. The expressions are also given in this slide and are available in IS 1893 part 1 2016 as well as standard textbooks on structural dynamics and earthquake engineering. After obtaining the value of P1, P2, P3, we shall obtain the value of modal mass as well, M1, M2 and M3. Again, our first mode itself contributes to 90% plus oscillation of the building, but for depiction we have taken all the three modes just for the sake of understanding. Now, once we have the dynamic properties ready with us, natural period, modes of oscillation, modal participation factor and modal mass, now it is time to calculate the design lateral force at floor I in mode K. This is the expression given to us. It looks complicated, but it is very easy. If you could follow what is happening in this slide, then you shall appreciate that this expression is quite easy. Now, in this case, for first mode the natural period is 0.380 second, which means that the value of SA by G shall be 2.5 given that the soil is a hard soil site. Then the value of AH1 is calculated, value of P1 is also calculated, and finally we get some the value of design lateral force at various floors in first mode, and similarly for the second mode and the third mode also. So, we do it to find out the design lateral force at various floors in various modes. Now, we shall look forward to combine these modes. How should we combine that? First of all, we need to calculate the story shear forces. How do you calculate a story shear? The story shear in any story shall be equal to the sum of all the forces acting above that story. So, with that we have been able to calculate the story shear force in various modes, modes 1, 2 and 3, and then we have combined all the modes through SRSS combination, that is a square root of sum of squares, which we have calculated it over here. And the design lateral force at floor I considering all the modes shall be obtained as the difference between the story shear force for story above and below the floor. Now, once we have found out this, let us represent it through a schematic diagram for design sizing force on various floors and design story shear. As you can see, the design story shear in the middle story shall be equal to 33.47 plus 54.53 kilonewton, and therefore you are able to obtain the design sizing force and the design story shear. Now, we have estimated the design sizing force as well as design story shear considering all the modes. Now, if we want to distribute it among various lateral load resisting elements such as columns and shear wall, then if your slab provides you rigid diaphragm action, then you can distribute it in proportion to the stiffness of various lateral load resisting elements. But if your slab is unable to provide you rigid diaphragm action, then in that case you have to consider the flexibility of the diaphragm or follow other global codes which suggest to distribute it in proportion to the tributary area. This distribution, this in-plane distribution of story shear is very similar to what we do in case of equivalent static method. With this, we will stop at this point and see you in the next class. Thank you.